Thank you for coming this evening, and we're very, grateful to VSC, Toto, and Bose for hosting us here. I should say this is one of the best showrooms. For Hong Kong, it's very, very spacious and a nice place. And we have a fantastic topic today, advanced materials. And I think Christine will later talk about how this started. But I just wanted to give you a brief overview of what's coming up, and which is party time for AIA Hong Kong. It's happening soon, December 9th. And please do join us there in Quarry Bay. And it should be a fun event with music, dancing, and food and plenty. So hope to see all of you there. And I just will go over a little bit briefly about some of the events we've been having. The building, the M+, which is actually underway right now. We had the exhibition and tour of the winning entries at that time. We also had the quarterly with Moshe Safdie, which was actually very good in Asia Society. Then we had a fun event on jazz recording to understand about music, and also a technical seminar on optimizing office space, a brain trust series on innovation, inspiration, and invention. And it was well attended, as you can see. We also do some learning, which is the ARE examination that has come to Hong Kong, which is, I think a lot of members are actually preparing and taking it, so it's very convenient. The building tours, like the one to Jockey Club, Innovation Tower, the Heritage Comics Home Base, and also the Oil Street Tour for the historic structures there. And we had also experimental green strategies, an event on that, some international approaches to energy performance, so on sustainability. And we had our grand party at PMQ, and so some of you who are not aware, you should visit this place. It's quite nice. In fact, yesterday there was an event as part of Detour, which was quite interesting on heritage conservation. The grand party, I think we had about 250 people attending. It was a fun event. And the Asia Cities Symposium, which was in September, this is something very interesting, and I just heard somebody tell me that it needs to become an annual event, and I think it will happen. So watch for this next year as well. And we had something on Dubai, the city of dreams, and the adaptive city, and the other major event for AIA, which is the Honors and Awards, which was well attended, a lot of awards. And at this point, I'll give it over to Christine, our IR president, and she'll talk a little bit about the advanced materials. Thank you.
That's definitely the highlight. I just want to say a few words. First of all, I don't know if you know what the IR is. That's the International Region, which is actually combining all of the members who do not live in the United States so that we can come together and do events like this. Hong Kong is wonderfully developed. We have a lot of events. We're now trying to reach out to many places, many of our neighbors, Singapore. We have Shanghai now. I don't know if you're aware. Beijing is coming. So get involved and stay tuned, and your colleagues around the world can also join us. But bringing us to what I really wanted to share with you, advanced materials is a concept that Ted Givens, who you'll hear from shortly, really, through discussions, we really felt that our role is to bring you what is relevant in our profession, what is happening, what's new, so that you can be at the forefront. You're not learning from others, but you actually are bringing that knowledge to your clients, to the profession, and going back to those creators and engineers and saying, you know, what I really need is something that does this or this, and so that it becomes the architect's part of actually really creating and shaping these new materials and advanced materials. Christian then, our current president, who apologizes, he wanted to be with us, he's in Singapore, he took this as a focus for this year, and he's really been bringing these together. I won't read all of these. In fact, this is just to share with you that we actually began this, was it 2 years ago now? and we started this discussion working with special materials, and you'll see some of them actually implemented in some of the work you'll see later. We started this, and we got such a positive response to being at the forefront, learning about new materials, understanding technologies, that this whole year's program came forward. This is the one that we did earlier this year, and this had to do with graphene and smart concrete. We had some very bright engineers sharing different materials with us, and I was just talking that I really hope some of these become usable, because I'd like to specify them, and we need to work with them. And we talked a lot about these materials. We are actually doing a write-up, and thanks to VSC's support, we've been able to do this year's series, and we'll also be able to raise some awareness for what we've learned and how that gets shared with others of our colleagues. We then had our second event, which had to do with advanced facade design and applications, and we started to learn a bit more, some of the other advanced materials, and I hope some of you were there. If you weren't, this will also be part 2 of this write-up. And this is the people that shared with us and how they shared. Some excellent. And today is part 3 in this tripartite series. Again, my role here today is 2. I want to first introduce our sponsor, who's going to say a few words. And again, we couldn't do this without VSC, and the support earlier was with Banyo Design and now with Toto. We really appreciate that support, and I hope that you all recognize that we can't do this alone. It's a real partnership. And after, I'd like to ask VSC Representative Alan to say a few words, and then I'll introduce our next speaker.
Thank you, Christine. I'm Alan. Nice to meet you guys. I hope you enjoy tonight's evening with food, with the topic, of course, and with the space that we offered this time. I hope you guys will have a wonderful experience tonight, and thank you very much for your coming. Thank you.
Thank you again, Alan, and to everybody who's made today possible. We know that there's a lot of little pieces that go into these evenings. Without further ado, I'd like to actually introduce Ted Givens. Ted has been an active member of our chapter here in Hong Kong, and as I said, he's been a brainstormer about new ideas, creativity, advanced materials. He is a partner with 10 Design now, but he's also really leading towards sustainability and innovation, and he's really brought some interesting ideas, both personally and professionally, to the discussions that our chapter is having, and so we're really indebted to his energy, and like him to introduce our speakers today. Thank you, Ted.
Yeah, Christine and I have been working on these ideas for a long time, and I think kind of using the AIA as a medium to make it open for discussion and to really help bring awareness and push for that. And we have some good local speakers here with us tonight. I think it's kind of interesting to know what's happening in your backyard. There's some really innovative projects and minds at work in Hong Kong. I don't think people realize that. And I think it crystallized around kind of the Smart Geometry Conference. That's how that started. Both Christoph and Carlo were Jason were quite involved in that process. And then we have Warith Zaki speaking tonight. And he is one of the kind of key designers at TIN. And he works with robotics. I think he's got some very, very innovative things. We have Christoph Krola, who also is involved with smart geometry. And he's a teacher at Chinese University of Hong Kong. Also has a firm, Lead Architects. And Jason Carlo of Hong Kong University. He leads the master's program, was one of the, the cluster leaders at Smart Geometry, and has his own firm, Carlo Architecture and Design. So just excited to hear what these guys had to say. I think we'll start with Jason.
Thanks, Ted. Hey, everyone. Yeah, I think interesting to be part of a conversation, ongoing conversation on materials, and I think what many of us will be presenting tonight is about materials, but also about the tools with which we work with materials. I'm going to start with our, a presentation that will touch on the cluster that we did at Smart Geometry in July. We have another cluster champion here, Ramon van der Heijden. Thanks. And our other partners, Alan Tai, Christian Lang, and Gustav Fagerström couldn't be here tonight because two are in New York, and Alan must be working hard because Ramon's here. But I think I'm going to go, before I get to the work in Smart Geometry and our cluster, which was called Smart Towers, I'm going to talk a little bit about the background research which leads up to this. This is not, no, there. Christian Lang and I have been teaching at Hong Kong U for a number of years, and we've been working on a research project which is developed into a book project called Cities of Repetition. The Cities of Repetition project has been looking at a number of large-scale, privately developed housing estates in Hong Kong. This research has grown out of our interest in housing and also computation, and it's become a platform in looking at these housing estates to understand how production, architectural production, has driven built form in Hong Kong. And then it's got us thinking about how new means of production and design using the computer can start to maybe change or alter the ways that these estates or housing could be built in the future. So in the book project, we've been looking at a number of these estates with multiple towers that have been built between the 1960s all the way to recent decades. And we're mapping them and remodeling them with, well, photography. And then we're also building these large 3D models of each estate and starting to dissect them in different ways. So we've been collecting and reproducing every tower floor plan. We've been looking at, we've basically redrawn every unit in all of these estates across, well, 9 of these estates across Hong Kong. And we're looking to find similarities in terms of families of units, families of towers, how strategies for building cores and fire exits have developed, and basically start to understand these relatively repetitive environments, how they're repetitive and actually how they start to vary. Some of these large estates actually have hundreds of varieties of housing units that are developed into different families. We're using different drawing techniques to start to pull this, again, the estates apart, switching scales from the urban to the tower, all the way to the housing unit. Part of my research has become interested in not only the units of housing, but the modules of architecture that start to form housing. The projected window has been one of my areas of interest for the past few years, which is something that's been tightly regulated and controlled in Hong Kong. There are incentives for windows like this for their fabrication and prefabrication in the Pearl River Delta that make buildings more sustainable through their off-site production. So in a project that I completed in the past year, this is a Hong Kong single occupancy strip project. We started with a typical Hong Kong floor plan from a tower and basically stretched it out into a linear mode of architecture kind of along the facade itself, understanding what elements of the facade projected out and what living spaces could project in. And then using Rhino and parametric tools like Grasshopper, we started to think about how windows and facades could be subtly changed to not be so repetitive, but start to account for programs on the inside, eating, sleeping, working, and also views and relationships to sunshine and solar orientation on the outside. So this was a project that basically formed a catalog of window types that could then be applied back to housing towers. This was featured in the Hong Kong Shenzhen Biennale last year as a single strip for a single individual, which then could be kind of stacked and then applied to the side of a building. Likewise, in the teaching work at Hong Kong U, we've been looking at how you could start with typical tower forms and then start to alter them through, again, computation. How you could start to change from floor to floor, starting to change unit sizes to accommodate for different families or people on the inside, to think about the thickness of the facade, to think about, again, how subtle variation through adjustments in floor plates could start to accommodate different activities within the facade. To think about how buildings might be hybrids between residential and commercial, and how the facades, again, might reflect that in their orientation, their thickness, and their density. So these were a series of projects in a studio called Shell Game, which looked at basically designing the facade of a building first and then working back inwards towards the core and developing floor plans. Christian has also been working through a series of design studios at Hong Kong U that look at the entire housing estate, like the ones we were looking at in Cities of Repetition, to think about, again, how through parametric computational software we can start to adjust, redistribute density, redistribute units, and rethink the housing type in a manner that might not be so repetitive, which could offer different modes of living for different sorts of residents. So these were some student projects that came out of Christian's studio called Serial Architectures, Systems of Multiplicities, Rethinking Podium Tower Urbanism. Again, thinking about how connections might start to be made between towers, not just at the ground level or the podium level, but at higher levels within housing estates, to introduce different functions into different levels of the estate, how building masses might be redistributed or offset to create different types of balconies or courtyards that might not exist under the strict building codes that we have in place today in Hong Kong. So each of these design iterations comes with a set of basically coding tools which start to kind of push back against some of the building codes that we have in Hong Kong too. So this idea of digital codes and department or building department codes. Christian's been looking at this in terms of his massing. This is a series of projects developed by his firm Rocker Lang Architects that were in the Shenzhen Hong Kong Biennale a couple of years ago, looking at using the distribution of different types of mass vertically to create towers with different types of porosity, or towers that can be interconnected, again, differently with different types of floor plans layered on top of each other, to, again, introduce a type of urbanism into housing estates which today are almost purely residential. So these ideas that we've been researching and working on in our individual studios within school and our personal firms all contributed to the idea to propose a cluster for smart geometry. The cluster actually took two different threads. Christian and I, along with Ramon, Alan, and Gustav, basically ended up looking at Hong Kong towers in terms of two different means. Right? The Hong Kong Smart Tower cluster was broken into two groups of researchers and participants, some looking at the way that tower systems could be constructed and remodeled, and others looking at actually mining the data from existing towers. I'll talk a little bit about this one first. Ramon, who's in the audience tonight, was kind of the driving force between this one. And actually both of the sides of the cluster used a plugin for Grasshopper that Ramon has developed. So Elephant, and I'm sure Ramon could probably tell you more about this after I'm done, is a plugin for Grasshopper that basically manages data and can map attributes into 3D geometry. Right? This is a program that where, as in Ramon's words, the Rhino model becomes a database where each object knows what it is, what it belongs to, where it should go, how big it is, when it needs to be fabricated, etc. Right? Ramon, of course, is working at Front. Martin Rees is also here tonight. Facade specialists in Hong Kong and internationally, where this software helps their production every day to make the workflow of complex facade systems much faster. So both groups were looking at different ways of using this plugin in particular. In the data mining side, they were actually looking at using unmanned aerial vehicles, or these kind of helidrones, or drones, to basically scan existing towers and pull data onto them and actually create BIM models of buildings through sensors that Ramon and his team built onto these quadcopters. So for about 3 days in July, right before Typhoon number 3 rolled in, these towers were actually, or these drones were scanning a tower on the campus of CUHK. And in doing so, the tower pulled back visual data, which enabled them to create very accurate 3D models and basically start to pull off real-time data from those. So this is a mapping of the temperature using a laser thermometer scanning the facade of a building on the campus of CUHK. Basically, the drone was flown up and down to scan the information and then feed that back into a 3D model. So this was kind of one way in which, through this kind of scanning and mining of data, it was fed back and then actually mapped onto each pixel, basically within, or element within the 3D digital model. The other group was looking at using Elefront and, again, parametric softwares with Grasshopper a little bit differently. So in the data construction group, again, we were looking back at a series of housing estates. In particular, Christian and I have kind of come up with 3 types of planning strategies that we found in Hong Kong. In the smart geometry group, we were looking at the strip, these kind of linear strips of housing that form a kind of wall effect that most of us are probably very familiar with in Hong Kong. So projects like Caribbean Coast, where you have a series of buildings very closely arrayed to one another that create a wall to ventilation in the city and block views potentially for buildings behind. You know, this building typology occurs all over the city. So we were interested in looking at, again, ways to alter that building form or that urban form. The OMA Stock Exchange in Shenzhen was one precedent for us in looking at how it could pick the podium up off the ground. Another precedent for us in terms of fabrication was the Sky City Tower that was proposed and prototypes were built of in China, in Changsha, which was proposed to be one of the world's tallest buildings made out of prefabricated frames. So we were looking at how, during the 3-day workshop, we might use similar frames and elements to construct towers. And then, of course, in Hong Kong, we're also very interested with connectivity. So connectivity became interesting to us as well. So over the course of this 3 or 4 day workshop, we worked with cluster participants to take a prearranged set of building floor plans or typical floor plans or profiles, like an H block or a kind of a cruciform shape that we're familiar with in terms of tower designs, and wrote a Grasshopper definition that would start to give the participants the power to array those different floor plates on top of each other in ways in which offer them different value systems within the building. More connectivity, more porosity, more public space that could be distributed higher in the tower. And throughout the first 2 days, we generated all of these digital versions, which again were assessed by the cluster participants in different ways, right? More living space. We started thinking about these terrace areas as potential kind of public spaces within the towers. We chose a series of those for modeling, and then we used 3D printers on site to begin to make prototypes or physical prototypes of those. And then using Elefront, we were able not only to generate these towers and manipulate the towers very easily, but we were able to pull out quantitative information about the towers. Again, about how many beams and columns each one was using, how many platforms or square meters of public space each tower offered, how many subdivisions or joints each of these towers had. So the Elefront plugin offered this very powerful tool to align the tower designs with the kind of bucket of parts that we had prefabricated for the participants to build models with. We used a very simple column and beam system with a 3D printed joint to make models. So in advance of the cluster, Christian and I had printed thousands of these little kind of custom Lego pieces in the 3D printers at the University of Hong Kong, and laser cut thousands of beams that would plug into them so that we could basically start to assemble layer by layer using plans that were output from the Grasshopper definition and Elefron, each tower. So these were the structural systems that we ended up with. The participants could start to control how the towers were offset from each other so that they could start to develop different floor plans for the kind of the small housing estate. Each tower could be controlled in height and again in terms of floor plans and profiles. And then as the kind of last part of the workshop, we started to think about how the skin might be another element that we could control during this few days of a workshop. The ultimate goal was to take the data that Ramon and Alan and Gustav were mining from towers in Hong Kong and try to map that back onto the towers that we were designing so that both halves of the cluster would start to exchange information at the end. But we realized that 4 days wasn't quite enough to do that. But the idea is still there that we could potentially map data onto the facades, or the facades of the towers could start to contain information that related to temperature or wind or solar exposure. So we developed these kind of facade panels that were all different and made out of plastic sheets that responded to a sort of digital input. So we oriented this point in space, and all of the panels sort of could reorient to that point. So basically large panels to small panels and different colored panels could be kind of custom distributed around the tower based on where the position of this point in space was. So it's kind of a theoretical idea and kind of testing how through that software and the model the panels might be redistributed. And then those were built onto the models, and after a couple of late nights at the end, these were the final results. I think that's it. Thanks very much.
Hi everybody, I'm Christoph Krola. Thank you very much for having me. Thanks, Ted, for the invite. I'm an assistant professor at the Chinese University of Hong Kong. I'm the founding partner of the Laboratory for Explorative Architecture and Design. I'll show you, well, my colleague Mark Schnabel was originally going to join today to present the Smart Geometry Conference a bit more broadly and in depth because he was, together with me, the host of the event. But he was the main man behind it, but he miscalculated the date that his child was going to be born, and I think they're in the hospital right now. So with that, that's as an excuse why I'm actually not showing anything from Smart Geometry. So I'm just going to share a little bit of my own research work that I've done in the past 4 years since I moved to Hong Kong through both university and my office. I'll start by briefly sketching the context in which I operate, and I'll share 3 projects with you briefly. I'll start, if this works, yes. I'll start with this slide, which shows the exponential growth in microprocessor transistor counts that you have available nowadays. This is Moore's law, which basically says that computational power grows exponentially. This slide shows hard disk capacity. My first computer was around here when we had around 100 megabytes on our huge hard disk. And nowadays on my phone I have 128 gigabytes. So just to say that if our grandparents back in the day, it was unimaginable what we would be able to compute nowadays. In a similar way, for us, it's totally unimaginable where we're going to end up in 10, 20, 30 years. So in a way, we're in a context similar to molecular cuisine, where we have all these new types of tools available, where we can create new flavors, new tastes that we never tasted before. And that's the environment where architecture is heading towards, potentially. And you start to see it in extreme geometries that pop up all over the world, Fuchsas, or with extreme speed with which projects like, for example, the Sagrada Familia are now going to be able to be finished 30, 40 years ahead of schedule, or strange new neo-Baroque experiments with plastic shark toys that are being recycled into fountains pop up, or big alien objects that arrive in our cityscapes with an unprecedented level of detail and sophistication that makes them absolutely alien to the human world up until fairly recently. Of course, all the techniques and tools that we know within digital fabrication make this possible. CNC mills, water jet cutters, plasma jet cutters, and the software such as BIM allow us to actually manage these vast amounts of geometry and data in a very controlled way to allow us to build new types of architecture. I used to work at Zaha's before moving here, and I had a great time doing that. Coming here and trying to set up my own thing, I also realized that this is a lie. The vast majority of the projects will never ever have access to that. And in a way, just to quote Ford Gibson, the future is already here, it's just very unevenly distributed. And unless you're part of a thin layer, you won't have full access to that. And that's where I try to frame my work. I'm trying to critically explore how the virtual unlimited freedom that we have in the digital, because computational power is conceptually for free, it allows us to design and draw anything that we build, that we want, and we can theoretically build anything that we want. How that world can be met with a very restricted and often unevenly distributed physical reality where skills are not the same all over the world, timelines are different, materials that are not available in the same way. So that's where I've been trying to figure out where digital techniques can be appropriated most strategically to allow for a little bit of that magic from the digital that we all get so excited about, to get a little bit of that magic to trickle down into the build context that I'm still restricted to. So the first project I'll show you is a fun competition that we won a few years ago, a project that we entered as a joke. It was the Golden Moon 2012 Mid-Autumn Festival Lantern. I don't know, maybe some of you saw it. Statistically speaking, quite a few of you should have been there. It was a very popular installation that we built in Hong Kong 2 years ago. It's a long story why we ended up with a project called the Golden Moon. Believe me if I tell you that it's a joke when we entered it. We basically just wanted to make a big fireball in Victoria Park. There's a whole legend behind it. I'll spare you the details there. One of the real, oh, sorry, I hope this works. One of the real drivers behind this, I remember this pretty disturbing video of Bucky Fuller's Montreal Biosphere that caught fire after an illegal welding took place. Nobody got hurt in the process, but I always thought it was a very powerful image, and it would be fun to see if we could do something like that in Hong Kong, and then if people would be able to enter it. It's a test in workflow. The client called us, told us that we won, and they also presented us with this schedule. This is a 20-meter fireball. They presented us with this schedule, giving us 3 weeks to make tender documents, then a month to go through public tender, and 3 weeks for prefabrication. Only at that point will we know who we're going to be working with. 11 days for construction, 6 days for display to the public, and then 1 day for demolition. So in Hong Kong. So it was an interesting challenge to move forward. Well, this is the design. It's basically a structure that sits inside a reflection pool that has a walkway running through it. And it consists of the following elements. We're not allowed to have any foundations. It's built on a football pitch. So we started off with a steel base that was weighed down with a concrete slab to prevent it from flying around. And then a geodesic double-curved or single-curved member steel dome was put on top of it that was wrapped with 2 kilometers of bamboo in a diagrid, spherical diagrid, and then 475 unique geometry flames were supposed to be wrapped on top of that. Became quite a logistical challenge to find ways to communicate this with the people that built it in the end. But luckily we're in this part of the town. The contractor was very brave and probably underestimated the responsibility that he took because he didn't realize it was a design-build contract that he signed. He took us to a Guangzhou shipyard just across the border where they usually build 200-meter-long container ships, around 20 per year, roll off or out of the harbor. These are entirely built manually. There's no CNC involved whatsoever. So we made drawings for them that looked like this. Constant radius because it's a sphere, everything nicely numbered and labeled. These were the nodes that were all unique. And these points are the intersection points of the steel and the grid. It was made using this very manual machine, 2 rollers and a heated coil in the back that basically put a current through the steel, and they squeezed it through it and rolled it. These were all the pipes when we visited their factory. And when I asked them what these guys were doing, they really tried to push us out of the factory, but I insisted. And what they're doing here is they had with chalk marked out what the radius of the sphere should be. This guy has an ice bucket, and the other guy has a blowtorch, and they're manually adjusting the radius of these steel pipes. When I asked them if everything was going to fit, because it's pretty tight, they said, we'll see on site, because there's no time for prefabrication. So everything was prefabricated, everything was nicely labeled, everything was nicely numbered, then everything was painted, then everything was numbered again, because they overpainted the numbers. And then in 3 days, they assembled the dome, which luckily fits. But just to give you a sense of scale, this is 6 meters. This is us frantically trying to keep track of whether or not the members are installed in the correct way. And on top of that, a diagrid, 2 kilometers of bamboo, as I mentioned. Fantastic material. I became a bit obsessed with it since. Specifically for this reason, in Hong Kong, the Cantonese part of the world, Hong Kong, Guangzhou, Macau, is the only part where bamboo is used for scaffolding. They build with bamboo in Indonesia, but they use steel scaffolding. Here's the opposite way around. So these people, they don't use plans or drawings. They do to make an outline of where they need to go, but they follow rules of thumb and experience to basically make their skyscrapers, all with just simple plastic ties. So we worked with these people to figure out how, with a grass material, with various lengths, various diameters, various properties, we could still make this diagrid. These were our construction drawings, simple prints, varying stick lengths that would be able to be absorbing, would be absorbed inside a stick. All the markings of all the intersections automatically extracted from our computer models. Here you see the very high-tech fabrication and everything being installed. The grids that you see are the temporary scaffolding, and the diagonal lines that start to appear are them matching the markers on the steel with the bamboo. And gradually you see the whole thing emerge. Amazing acrobats. They all wear safety belts, but they don't hook them up to anything. Here you see them at the top trying to match the final pieces of geometry. Then the flames. We initially had a white lantern, but that's apparently only for funerals here. So we had to add 8 colors to the 475 geometries that we have. And there we designed a paramorph setup where we design basically a shape. It's made from stretch fabric, electrical tubing, and bamboo. A shape that can adapt to various setups. So these 475 were snapped down to the 10 most common averages of geometries that would then be able to adapt to the changes in the geometry to begin with, and to the give and take 20 centimeter construction tolerance that we had on site. Everything came in nicely fabricated in the new territories. Very simple detailing, again, electrical tubing, zip ties, and slowly everything was installed on the bamboo using the diagrid as a guide. These umbilical cords that you see hanging here are 10,000 LED lights that had to be installed in parallel on top of that to make a spherical screen on an imprecise and accurate diagrid of bamboo on top of the steel structure. This is day 11, almost finished, where you see it in the context in the park. Just had a rainstorm here that saved us 40,000 Hong Kong dollars of water because the pool filled up by itself. But it cost us 8 hours of working time. Here you see them adjusting the final angle of all the flames. And this is the installation right around the time when we got permission to start construction. So 3 hours before opening. Up until then, we were in an illegal construction site. And this is the final piece. So you see that the diagrid of the bamboo disappears entirely because it's absorbed in the geometry of the flames. The very harsh gradient in the colors disappears because of the LEDs that come through it. And it became a very fun and exciting night. We had to triple the queuing lanes because we had 400,000 people coming in 6 days. And here you see the slowly we're moving inside where, so just to get a sense of scale. So the competition brief asked for lanterns inside lanterns. That's why we have these large scaled up version of your children's pop-up lanterns hanging inside of it. These were swaying in the air. The diagrid was swooping around it. The light show was animated. And because of all of these, your sense of depth totally got scrambled up as you entered the space. So it was really a nice experience as you moved in to sort of be swept away by the whole thing. A really fun experience. The nicest thing about it was that it gave such a highly affective outcome that people could relate to quite well, and it was a very nicely popular event. We had some videos running over it with agents, etc. I can That's another half-hour lecture. But here you see the clash with the coloration in Hong Kong. So that was a very nice first experiment. Thank you to the sponsor. It was very well received. Almost as fun as this one, which was one that popped up in a highway in Changsha a year later from Mid-Autumn Festival, when somebody made an inflatable copy of our project. So interesting way of further appropriating a particular geometric idea. Oh, next project started, sorry. Oh. Okay, my slides got mixed up. I was supposed to do the explanation first. And this is a project called Breathing that we did for the RIBA in Shanghai for Xinjiandi, where we invited to make an installation for a sushi restaurant with a budget of 50,000 renminbi, so very, very little. And we decided to see if complex geometry could be built. So there's a lot of architectural questions of facading and cladding complex geometry embedded in there from the simplest of ways. And these are the only construction materials that we use on top of that one steel bar and the bladder that was moving inside. So we made it all out of laser cut, acrylic shingles, all the same shape, a simple nylon net, and these little clips from paper clips that were clipped in, and then 20 students that spent a night on it. The concept there was that the installation basically took one breath every 90 seconds. And the idea was that when people look at it, they'll be interested in seeing it, but after a few seconds they'll turn away, and just around that time, that's when they'll start to see that it's actually slowly breathing. So that was an interesting project that triggered some new ideas. I think the video is going to play again. I'll just skip over it. Yeah. All right, the next project, two more I'll show. Following up on the experience with the bamboo people before, this is something we're going to build in Hong Kong soon. I'm not allowed to tell you where officially, but maybe you can see it. This summer we'll build a new bamboo pavilion, and this comes out of a workshop with my students where we're looking into hyper lightweight structural systems and how we can basically reinvent this dyeing craft and give a new future or purpose for this dyeing craft in Hong Kong. They're really suffering in getting people that want to join in the bamboo scaffolding industry, and we thought that by giving it an architectural outcome where it's not just something temporary like the theaters or the scaffolding, but something permanent, then maybe the industry could be taken to a next level by bridging it and merging it with digital techniques. So this is a mock-up that we made from bamboo splits of a pavilion that in the end will span around 25 meters and be around 12 meters height. And it basically is a diagrid, a triangulated diagrid that folds onto itself in a tripod structure, and that because of that basically ticks off all the boxes of what you would need to be structurally sound. And then that's clad with a translucent fabric, slightly tensioned around the system, able to absorb all the geometric imprecisions, and basically protecting the bamboo from sun and rain, which should theoretically make it last forever. So a little video here that shows, I cannot, my bad. So here you see the triangular grid. So basically we programmed this geometry to react like a spring. All of these lines are sticks that try to straighten themselves out. And they're fighting the forces that we apply onto them. And in the meantime, they're negotiating their internal straightening force with the forces that we apply onto it. So it allows us to sort of mimic the general properties of bamboo. And here you see the overall construction sequence. It consists of a series of arches, very basic arches in the beginning, And once that structure is stable, then these tension membranes come in from the side. All of that will be clad with strips of fabric that still allow the wind to go through, so the whole thing doesn't blow away, because it's hyper lightweight. It's weighed down with 3 concrete plinths around the perimeter, and that's the final piece. So hopefully should be finished by Mid-Autumn Festival next year. And then, yes, this is the final one I'm going to show. This is a research project that I'm currently involved in with RMIT called Smart Nodes. It's exploring how 3D metal printing could be combined or applied within the architectural industry. It's part of the Independence Group, which is a research fellowship that I was granted, that came from the Architectural Association in London. And it was basically done in Melbourne with RMIT and partners from Arab there, and people like Professor Mike Shee, who is an inventor of evolutionary optimization. And just to explain what that is, the goal is to make a pavilion that combines extremely high-tech elements like 3D metal nodes with extremely low-tech materials like standard off-the-shelf timber and just flat sheet-based material. The idea being that anybody can design and order that equipment and then combine it with whatever they find in their backyard. But why 3D metal printing? A few things. This is a generic node from an Arab project from a tensegrity structure, and you can imagine this is quite difficult to fabricate and make. Now, Mike Shee is the inventor of evolutionary optimization or topological optimization, and the concept of what his software does, it basically breaks down any geometry into finite elements. You apply loads on it, and it removes the material that doesn't perform at its most. Like if you pull here and here and here, you can imagine that that part over here is not as actively performing as the steel right behind where you pull is performing. So what his software does, it basically translates a node into something like this, which is the minimum amount of steel that you would theoretically need to resist the forces that are applied to it. This is important because for 3D metal printing, geometry is cheap. It's the matter that costs you money. It's as easy to print something complex. It's as easy to print 500 different ones as it is to print one specific node. So if you have a 3D printer available, that allows you to change quite a few things on top of it making beautiful nodes. So these are earlier concepts, and this video shows what the pavilion eventually aims to do. So the idea is that you draw any outline, then manually you paint that mesh. We're really questioning the role of the author or the architect as well. And then from then on, automatically, a hexagonal grid populates the surface, inverted gravitational forces pop it up into an equilibrium surface. We have an automated structural analysis running through that gives you all the bending momentums in each and every one of the members, all the shear loads, all the axial loads, and basically for every node that we have inside the structure, we know what it needs to do in order to make this whole structure stand up. So this is still the shear forces. We can automatically figure out what the deflection would be under wind loads, various wind load scenarios. And then basically we zoom into each and every one of these nodes, we extract them from the geometry. We put a sphere on top of that we then evolutionary optimize. And in that final node, we have all the geometry embedded to allow a super easy, very user-friendly connection with standardized steel plates, etc., by people on site with no plans, no skills, no nothing. This is the model that we presented last week in Melbourne, where it's done with plastic printers. For this one, at the 1:5 scale, where we have 144 different nodes basically throughout the system. And as you can see, it allows you to not only absorb the different geometries that you have coming in, solving a big problem of node-based space frame structures, but you can see how different loads give you different geometries in the node itself as well. How here, for example, clearly there's a very small force here and a larger force over there. Twisting beams make no problem whatsoever. Whether you have 3 or 5 nodes, it only becomes a little bit more tricky in how you assemble it. But these are plastic nodes made on a small scale. In the same time, we were testing how a steel node could theoretically respond. And these are the types of geometries that come from it. So it's very exciting because there's no designer involved in these really. We set up the parameters and it's pure material properties that drive the entire outcome. So here you see another one. Sometimes it becomes very standard. This is the first aluminum one that we printed. This is one of the first steel ones that we printed. All kinds of other issues and problems start to appear. This technology is still in its early stages, but patents have expired this year. So similar to how there's been a huge drop in cost in plastic printers, there's an anticipation and prediction that within 5-10 years, these techniques are going to be able to compete with manually fabricated nodes. In parallel to that, we're looking into ways of how complex geometry can be panelized with flat faceted elements as well. So this is a study model, a precedent of the previous one that my students at CUHK made last fall, where all the panels are also totally planar and all the nodes are still 3D printed as well. So what I'm interested in is that in spite of automation and the prolific use of computation everywhere, construction still remains a human enterprise, by which I'm going to toss a ball to you, that robotics, in my mind, are not yet that far. They are still too far dissociated from the construction to have a large-scale impact. But by strategically applying digital design and fabrication, and a plotter can be a digital fabrication tool, as I've shown you before, there's various ways to allow you to have some of that magic from the digital world trickle into the construction industry without a high investment cost, without a high material cost. Thank you very much.
Thank you, Christoph. Oh, hello, good evening, everyone. So my name is Warizaki. I'm actually a designer at 10 Design. I've got a couple of my bosses here looking at me. So yeah, I'm a bit nervous now. So, well, thank you very much. I've been highly inspired by the talks from Christoph and Jason, and I'm starting to question my presence here now. Very, very inspiring stuff. So basically, I was working for a robotic workshop in London back in 2012. The workshop was involved in taking out research for sheet metal forming. So we were basically obsessed on sheet metal, a piece of aluminium that is about 3 millimeters thick. So what we wanted to do was to sort of find a way of how to form sheet metal in a different process instead of using the normal, the standard way of forming. Sorry. Oh, okay, sorry. Yeah, so this is a standard way of forming a sheet metal where you have a male and female mold. You put the piece of sheet of metal in the middle and then just press it. So it is very unnatural. It's not what the material wants to do. So what we come up with is, what we were trying to push forward is the basically a natural way of forming a steel metal sculpture. So basically what we were involved with was called curve folding. It's like playing origami with a metal sheet. And then we use robots to fold those metal sheets. So just to give an idea of what we do, I'm going to play a video of a project that we did to create a chair.
Videos are slow.
Oh, okay. It's not playing. If we're lucky, so this is one of the prototype of robots that we came up with, mini robots that picks up a steel piece of sheet metal and then shape it into a chair. basically, that's what RoboFold is about. We're about taking a metal sheet and form it through robotic use. So this is the final product of the chair. And then at a larger scale, this is how it looked like. Just press.
Or you may want to stand a little bit back.
Oh, okay.
No,
Oh, I'm
the other
sorry.
way, because you can't see.
I'm sorry. What's happening? So we were experimenting with a facade sculpture. We had a CNC router in the workshop. And we cut it into shape and score some lines on the metal, and then use a large robotic arms to fold it.
Ready by the stop button, just to pause the other one.
So basically, there are two large robots that have suction cups at the end of the arm, and then it picks up the metal sheet and then bring it into the other suction cups and then start to fold it.
Okay.
So the research started with an animation software, which is Maya. So the way we did it was we actually captured the frame, the animation frame from the software, and that is why you see that the robot is actually moving like a sequence, a frame sequence. But we have developed a software which is a lot more fluid at the moment, so it will be a lot more faster than this. It's very slow. Okay, so this is the final product for that piece of metal sheet just now. So yeah, back in summer 2012, we were approached by Zaha Hadid, specifically by their computational group called CODE, which is led by Shajay Bhushan. And at the moment, Shajay Bhushan and RoboFold are teaching at the ADRL. They're having their own studio. So basically, Shajay came up to us and he presented us with his idea of creating, Zaha had his idea of creating a sculpture, a shell sculpture that is totally made out of a steel metal sheet without the need of columns or beams. So they designed it and they gave us the data of how we want each piece of the metal to be folded, I mean, in terms of the angles and all. So we were not in the process, we were not part of the process in the design. They came up with everything. They gave us the data, which is in a text-based file. We put it into the software and then start fabricating it. So there were about 480 unique pieces, and it took about, I think, 3 months to fabricate it. So this is some of the photos. That's Greg. Basically he started RoboFold. Gregory Ebt. So that's the final piece. It's made out of 480 aluminum seal sheet panels folded by the robots. So what I'm trying to show you today is how we make things in RoboFold. My presentation is not so much about theory, but more on the making things, like how the steps of making things that we do in the workshops. So we start with a paper, folding with paper. Sorry. So basically, in this workshop, it's very we have a lot of papers on the table, and we start folding it like origami, and then from there we bring it into Rhino, and then we start to identify where is the score lines that we can use to fold this steel sheet metal, and then we bring it into Rhino. We develop our own software called King Kong. So basically, King Kong is the software that will translate the design into robotic languages, so that the robotics can take the steel metal sheet and fold it into shape. So this is me, and you can see that's some of the products that we did behind. So we were playing with a lot of papers every day, trying to find the most optimum shape that we can build with robots. And then we came up with a few prototypes. This is 3 final prototypes that we wanted to build. It took us about 1 week to build this whole project, a facade installation in London. So yeah, we brought it into Rhino, and with the use of computation, we produce some sort of a instruction for the robots. As you can see here, this is how the robot is going. This is how the robot see the geometry is going to be folded. So it's it's in a sequence of animation. So that's why you see the robots just now as being, staggering. So, and then with the use of King Kong Grasshopper, we can also design a facade based on the parameters of scaling, rotating, and also the angle of folding. So before bringing it to robots, we had to manually test it ourselves because, as you can see just now, it takes a lot of effort and also time to test everything with a large robotic arm. So we wanted to cut the time, and then we make our own robotic arms, trying to determine where will the suction cup spots will be on the steel sheet. So, and then, okay, this is supposed to be a video. Is it playing? So then we send the instructions to the robotic software, King Kong, and King Kong will actually calculate the movement of the robotics in XYZ coordination. So this is the final product, the final scale that we wanted to build. Send it to the robots. We cut the metal sheet with a CNC router, and we also scored some lines on the metal sheet to be able to fold the metal. And then we also use our hands first before sending it to robots, because we tried to cut a lot of time as much as possible instead of leaving it to the robots to test it. And as you can see here, this is a prototype that was folded by hand. As you can see, there's a lot of inconsistencies because there's a lot of, we had like 3 people trying to bend the whole metal. So there was a lot of inconsistencies in terms of the pressure in different spots of the area. And the other one is folded by robots. So you can see it's immaculate. And then, yeah, we tested it on a different designs. Finally sending it to the robots to fold it. So picking up the sheet and folding it. So these are some of the facade metals that we produce. And in the end, we installed it on the wall in the workshop and presented it to the Bartlett School of Architecture a week after that. So right now it's nicely exhibited in the workshop hall. So, and then the second project I'm going to talk to you about is it's almost very different from what I was used to. So this one is about using computation means, but looking at how you can traditionally construct things. So back in April this year, I was approached by an organization in KL, in Malaysia. I'm from Malaysia. Right? So they wanted me to build an installation at one of their galleries. It's supposed to be it's supposed to be a backdrop installation, the only installation that's going to be there. So they sent me this photo, and I was excited to see it, and I was like, okay, that's a big space which I can play with. But then they say, no, you're not getting the whole space, you're getting that thing, that red area. Then I was like, what is that? There's not even an area, there's a wall. So so they're like, it's a marketplace. It's going to be a marketplace for designers where they can sell things of whatever they design. So, and then they want me to literally build a backdrop. So they gave me this area. It's basically just about 600 mm width, and then a whole stretch of the hall. And then when I saw this photo, I was like, okay, so you want me to build something that is going to block the only source of natural lighting into the hall? I was like, how's that going to happen? So they were like, yeah, just think of something. Okay. So one of the brief was to to design something that is heavily rooted to the Malaysian traditional architecture, instead of being too advanced in terms of concept. So I was like, okay, if I want to build installation, I don't want to block the lights. So what should I do? And then I started to look into things, and I found some photos of a traditional Malay house. So Malaysia is a tropical country, so it's very hot, and then we need to have a constant air ventilation. So in the traditional Malaysian house, we always have this kind of a screen, a light screen that allows air to come in, and also to allow lights to come in as well. So I was inspired by this. I was like, okay, maybe I can come up with something like this, a wall screen. And then also I was looking into more research, and I found out that in the traditional Malaysian architecture, we do not use any nails or any sort of instruments to build the architecture. Basically, we just use tongue and groove jointings. So I was like, okay, I'm going to take these two concepts and try to implement it into design. So I found a very old book holder in Malaysia. So, and then it uses the same kind of method for jointing, which is a tongue and groove. And then I dissect it and reconfigure the geometry for me to be able to create something that could be constructed upwards. So I sent it to the CES. The idea is to create something that is, how would I say, parametric. And then the idea is also because the organizer was telling me that they want it to be playful. I was like, okay. So I came up with the idea of creating something that could be completely dissected and then reassembled on the day itself during the exhibition. So looking back here, what I came up with was 4 types of modular components, and then you can just simply, without the use of any hammer or any adhesive, you can just construct the whole thing, So, and then it also will create some sort of a very nice light and shadow play. So send it to the CNC machine, 3-axis router, and then, all right, it's another video. So this is the process of, all right. It was supposed to be a video, but it's okay. So basically, there were 600 panels, and we brought our laptop that day. We put on our Grasshopper, and then we asked people to play around with the software, and then they can straight away. The Grasshopper script will tell them the instructions of which pieces should you put in first, according to the sequence. And then in the end, you'll be able to build a full wall that is not blocking the light into the gallery, and also create some sort of a nice pattern. So this is the view from the top. So as you can see, the different density of the openings, and then so it's basically we successfully achieved in reinterpreting the old Malaysian light screen. So the next project I'm going to talk about is smart geometry, which happened about 2 months ago. And then one of my team members is actually working with Christoph, Julian Clis, right? Yeah, he was one of my team members. So I was involved in this group called the Variable Lightness of Being. It was led by a group of structural engineers from Bollinger and Groman. They were involved in a lot of Kopima Blau's project. So they have developed 2 softwares, which are Karamba and also Octopus. So the idea of this whole workshop is to Octopus. It's a plugin for Grasshopper. So the idea of this workshop is to fully use these 2 softwares to create something that can be built without any need of machineries. So, which I found very interesting, because coming from the robotics interest, I wanted to go into something that is more traditional and more approachable for common people. So, so the idea is to create a pavilion as light as possible using local materials. So we wanted to create something that could float initially, that could actually just fly. So we used a bamboo, a locally sourced material, and also a balloon, a weather balloon. So by using grasshopper and caramba and octopus, we tested a lot of the designs. And one of it is to see how do you want to use, how do you want to marry the bamboo and also the balloons in order to build a pavilion. So these are some of the methods that we look into. And then this is a video. So one of the members was trying to, we were playing with the compression to be able to create a strong column for the pavilion. And then next one is, oops, sorry. All right, so this is another method of joining the balloon and the bamboo, which is also a video. Still can't get this to work. As you can see, I think we are the only group in the whole smart geometries that did not use any 3D printers or laser cutters or anything at all. It was just human labor. And then, okay, actually we do have a machine. It's the most advanced in the whole workshop, I believe. It's a sewing machine that we got from Mongkok Ladies Market a day before. So we were using this to create a skin for the pavilion, which did not end up being put onto the pavilion because we didn't have time. But yeah. Test we did. So how do we approach the design? Basically, we sort of scanned the whole space that we were given, and then we randomly put a point cloud into that volume. And then from there, we choose which are the supporting points, which are the points that are going to be, which are going to touch the ground and support the whole structure. So we use Caramba and Octopus to achieve this. So as you can see here, the red dots are the ones showing that these are going to be the point of supports for the whole structure. So like I said, it was a matter of pushing the software to the limits. We did not want to come up with any predetermined form. So we let the competition process to decide it. So, and then from the Caramba is actually a software that actually calculates the strength of the properties of materials and tell you this whether the structure is possibly built. And then, as you can see in this slide here, there are some black sticks, which means that we're going to have to use more than just one bamboo sticks. So in Octopus, it's more of an optimization software where we were given like thousands of possibilities, and then we can choose from them according to a parameter that we want to achieve. So according to the software, we needed about 2,000 balloons to be able to lift up the whole pavilion, and we just had 60. So from that moment, we knew that it's not going to be floating. It's not going to fly at all. So we just went on with the project, and then a few more iterations of the designs, and then comes the fabrication, the numbering and all, and then again the most advanced machines that we use. It's we use the cardboards to calibrate the sizes of balloons. Yeah. There was no robots, there were just human hands to fold and cut bamboos, and we started to build the pavilions from ground to up. So I think we were the last group to leave the workshop. We left about 4 a.m. in the morning, just before the exhibition day. It was pure human labor. So. And then the idea is that we wanted to use this kind of structure to be able to shelter Hong Kong. And in the end, float. Well, that's about it. Thank you very much.
That was great. So just a few slides to show some of the research we do at 10. We're actually the 2 floors up. We're about 150 people now, and we try to kind of weave innovative design into our process. One thing we try to look at is natural disaster. I guess a lot of buildings don't reflect their environment, especially like in the Philippines. Every typhoon comes through and knocks down all the buildings. So we're trying to design architecture that responds to its context. So this actually started as a thesis project back in, I think, 98. It was the idea of a suburb that actually pushes itself down and is half buried in the ground, so it becomes kind of resistance to tornadoes in particular. So the house is half buried, it deals with the light, but there are troubles with this up-down metaphor, people not wanting to be buried. It had a kind of negative connotation. But actually the project ended up getting built in LA for an artist loft that could only get light from the 3rd floor. So it took on a life of its own. But that became more of this pod-like structure that was, at the time we were designing an advanced materials lab for a community college, and they had a Kevlar skin they were developing that was Kevlar, insulation Kevlar, and they were looking for uses, so we thought, well, we'll design a tornado-proof house for you guys. And the idea was the house actually goes into the ground, it's on hydraulics, so when a storm comes, the house comes down, closes up, and it is storm-proof. And there's a redundant safe structure in the base as well. And actually, it didn't work very well at all. It was just a kind of a concept idea, but it kind of got us thinking, and we were trying to combine like a Roman courtyard house, a pool, and simple geometries. But it was good for us because it got us thinking and it pushed some ideas. But that ultimately led, actually a client saw that and wanted to build it. There's a guy in Utica, Kansas, has a farm that he's had in his family for 200 years. And it's been destroyed, I think, 3 times by tornadoes. And I think the 3rd time it destroyed his pickup truck, so then he got serious and called us. But the idea was to do almost a Miesian house. It's very glass and light, and only the top structure is needs to kind of resist the forces of nature. So you can actually land a school bus on this roof, and it'll withstand the loads. So this piece just comes into the ground, and during a storm, it's completely flat, and the air passes right over. And then it's a glass roof as well. So when it's down, you still get light. But the idea is that when a storm comes, it gets out of harm's way, and it's completely safe. So this is kind of an idea of how the house works. There's 4 hydraulics in the corner, and there's a series of structural columns in the middle. So the structural columns actually take the load from the roof, and it doesn't hit the hydraulics. And there's also some kind of algae tubes, organic farms, and things in the basement as well. And we worked with Stephen Lau at Hong Kong U, did a lot of CFD, wind and pressure studies to make sure this house actually worked and would not. I guess the main problem was uplift, and we found out we'd actually designed the edge wrong, so it would have ripped the roof off during a storm. So we redesigned based on the CFD analysis. So this is the house when it's down, the house when it's up, and that's the owner. So he's got a new pickup truck, and the site's actually behind him. And I think he planted those trees when he was a kid, so he's very proud of the trees. But it's just kind of funny where these designs go. This was one we started maybe 6 years ago. And it was the idea of trying to use titanium dioxide, which is a photocatalytic coating, and it removes pollution and organic materials from the air. And at the time, it was still a bit unstable, and it would actually kind of eat the surface that it was on. But subsequently, it's been refined, and now it's getting mass-produced. But the idea for this tower was we coat a tower in this material. It's coated in PV cells, and at night, it clicks on a series of near UV lights, because the light creates a cleansing action. So this tower would clean the air 24 hours a day. And we studied the skin. We actually multiplied the skin and the envelope to create more surface for this material. And then we split the tower apart so every unit gets natural ventilation and it maximizes the surface area. And actually we use CFD to channel the wind through, so it maximizes the pull across the facade. It also cross-ventilates the units. And it was also designed so that when the air exhausts the units, it doesn't wick back up onto other units, because this was kind of not too long after SARS. So the idea was we wanted to naturally ventilate the building, but also vent the used air. And it was, we started doing a project in Malaysia, which is quite a simple project. But the client actually liked that idea. They actually hired us based on that concept. So currently, they've actually added it to these towers. So these towers are about 16 stories out of the ground, but they're coated in this titanium coating, and they're actually sourcing the UV lights now, so it will actually clean the air 24 hours a day. And there's statistics that if, I think if 50% of the facades in a city use this coating, it'll knock out 80% of the pollution. So it's kind of a simple building, but it's just an innovative material that can actually have a big impact. That was just some of the statistics. And this is the project under construction. And actually, it's good because it's one of our first kind of theoretical ideas that actually is being implemented. And at the same time, this client is very, very innovative. And we were just talking at our last meeting about some new ideas we're developing. And we've found a way to actually make kind of almost like the biodome, like an artificial atmosphere, a machine that will actually make atmosphere. So they're doing a new housing complex. So we're going to test the idea of actually making air for the buildings. So not purifying the air, but actually generating its own atmosphere. Because they have horrific fires in Indonesia that kind of pollute the air. So there's a way to actually have clean air in the housing complex that the building produces itself. So we're pretty excited to get started with that. And it's just really about having these ideas, the research, and trying to get these ideas implemented. I think that's what the AIA has tried to do as well. It's just kind of sharing like some of these wonderful ideas, the research collaboration, and that kind of creating synchronicities, and just kind of taking these ideas. And we've met some Hong Kong investors that are helping us now, and their idea is like it's like enough with the thunder, you have to have some lightning, you have to hit something, so it can kind of take on a life of its own. But the basic drivers for us are buildings that move beyond neutrality. They have to take care of themselves and the kind of dearth of bad buildings out there in the environment. They have to generate their own energy, control pollution, purify water. Also looking at the locations, especially in regards to storms and disasters. You can't really ignore that. It's really not an accident when the tornado alley gets destroyed every 3 or 4 years. It's more of a probability than an accident. And also being careful that we're not kind of dominated by our technology, which is ironic since our building's underground. But just really about how to get from kind of the manufacturing to the consumer, and hopefully by sharing some of these new materials and ideas, it will bridge that gap and make that a smoother process. And I guess the last thing is we're looking at new materials, even for the AA, maybe next year. The meta materials, which can actually bend light, so they make objects now that are they're invisible to gamma rays, so it actually refracts light and bends light around itself, so it makes objects invisible. Memory alloys, it can if you bend it, it goes back to its original state, original kind of design based on heat, different forces. It'll go back to its original state. Also, phase change materials that actually change state, like from a solid to a liquid that absorb and release heat. And aerogel insulation, which is here, which is I think the lightest material on Earth. It's I think 90% air, but it's got amazing insulative properties. And also graphene, which I think Toby Gill talked about as well, which is one of the strongest materials in the world. But just kind of bringing these materials to light, and some have been around since the 60s, but it's really just kind of taking, just kind of hitting its stride now. And then one thing we're playing with now is, I think what Christoph touched on as well, is almost a trickle-up theory, like going to the poorest communities on Earth and doing interventions. We're doing a study for a Philippine village. We're going to make an algae bioreactor that actually produces pig feed, because the community spends all their money on the pigs, and then they don't feed the kids, and the kids get sick, and they have to sell the pig to take care of the kids. So we're trying to make an algae bioreactor that is targeted for people that make less than 50 cents a day. So going to the kind of root of the problem and trying to use high technology and grow that up. So, a quick synopsis.
Wow, right? I mean, wow. So many exciting things that are happening. We now have a few minutes for you guys to ask some questions, and we're going to ask Vicky, who has helped us behind the scenes to bring this all together, if she wants to maybe kick that off. Thank you.
Well, thank you for all four speakers. This is really wonderful and totally putting me to shame. And with that, my first question is, the work that you have shown is heavily dependent on a digital process. So for most architects who did not professionally grow up with the digital process, do you think they have any chance to learn it?
Do you have a Facebook page?
I'm sorry, no, but I'm on LinkedIn. And I'm going to send you an invitation after this event.
Okay, well, then you're already on track. Yeah, I mean, the tools are becoming more and more user-friendly. So it's not an overcomable obstacle, or it shouldn't be, or not anymore. I mean, the technology we use in our iPhones or iPads, my grandparents are working with it, and what is possible now becomes easier and easier. The real scary part is the speed at which the generation after us, our students nowadays, the speed at which they pick it up. And that's maybe Moore's law as well. It's also going to go up exponential as well. So I share your fear, but trying to stay ahead of the curve, I guess.
Yeah, I think for those of us who are working in design and working in academia, the digital world has a lot of prospects for research. So it's very easy to find a research thread within such a broad range of, I don't know, software platforms and technologies to zero in on. But I think that many of the projects, including the ones we saw, all resort back to manual applications at some point, right, where the robot doesn't bend something all the way, or students need to put the models together, or bamboo contractors are wrapping pieces of bamboo or lashing them together. So I think it's interesting to think about, but part of our work is also thinking about the material and labor and economic repercussions of these technologies too. I'm also very interested in how you could start to think about digital or complex ideas or geometries in one place and then be able to transfer that somewhere else that doesn't either have the technology or has a completely different set of skills and tolerances.
Well, I think the question of whether you can still catch up with the technology or computer software, I think that's not a problem, because I myself came from universities that did not teach me any softwares at all. So we had to rely on a lot of online tutorials, and also myself, I tend to go into places that would share with me all this knowledge, like RoboFold and smart geometry and that kind of thing. So it's not really I don't think it's a problem to catch up at all.
Thank you.
I'm inclined to say two things. One, a good designer can work as well with clay as he can with a pencil. So in a way, if you're a good designer, there's nothing to be afraid of. But actually, I disagree with what I just said, because the challenge and the task that we are forced to deal with nowadays, being under pressure to produce more at higher speed, etc., I think without computation on any level, I think it's going to be very difficult to still keep up. And of course, in the entire process, there's managerial roles, and there's people that do the grunt of the work, and there's computer programmers that have knowledge that none of us have either. And there's a place for everything, but I think computational thinking, procedural thinking, is something that will no longer that you will no longer be able to exclude from anything that's going to happen next century or this century. That's going to have an impact. So even if you don't know the tools, that might be fine. But if the thinking is not geared towards a level of computation, I think you either need to be very, very lucky with the types of clients that you have, or you're going to have a hard time to move forward.
I have two questions. One is related to just follow up to what you just talked about. What do you think of the impact on real creativity, like, the mind thinking, or relying on, technology to do a lot of these things? And then the other question is for Jason, actually. I was very intrigued with like looking at it on an urban scale. You were very gentle by saying repetition. I would have said monotonous. In a lot of Hong Kong is like that in a lot of places. How do you take all this and actually really create that variety and diversity that really cities should have, and even building typologies that make up, cities?
Well, I think when we first approached the Cities of Repetition project, in a sense, it was as a critique of repetition and monotony that came out of a 20th century focus on mass production and the efficiency of mass production in a positive sense that could respond to things like housing crises in cities like Hong Kong. And although it was initially set up as a critique to that, I think the more that we looked at the various housing estates in Hong Kong, the more we began to fall in love with them and saw how well they worked in many cases, right? And then, as I said before, even within so much repetition and monotony, there actually is a fair amount of diversification between them. Some of the earlier estates like Mei Fu, which has over 90 towers, actually has over 100 unit types built within it that are hard to understand from the exterior, but are evident perhaps in the demographics of the people who live there. But I think as the pressures of land value and time and money all are working with each other in Hong Kong, some of the latter estates, or the ones that are built more recently, have fewer unit types. And I think it's been in the news a lot lately about how micro units are becoming more and more popular in Hong Kong, right? That people are getting squeezed and housing units are getting ever smaller. So I think we're trying to find within it, again, a sort of value in repetition and production. We're not saying that it's all bad. I think all of these processes involve efficiency, and mass production still plays a huge role in architecture all over the world. But also we're trying to identify things that from the physical environments may lead to other problems. And of course, think about how computational platforms could start to change and add value or add performance, whether that's aesthetic performance or some sort of societal performance, to these huge built environments that we all live in Hong Kong, right? That one developer often has control over. So it's really about trying to find value systems within that and not necessarily value variation over repetition all the time, but to look at how that affects our lives.
Could you repeat the question again? I was just
wondering, because when you teach also, there's a worry that like when you get too much into digital technology and everything, that somehow the way the brain works, innovation and everything, some of it might be like, how do you balance between the two? So you're not less thinking and more relying on technology?
I don't know if I'm going to answer it by what I'm going to say, but I'll give it a shot. If the question is geared towards agency and the role of the architect and the role of design, I think one of the biggest challenges that architects have been facing compared to, for example, automotive industry, is that we only usually design one building at a time, and we pour our heart and souls in there, and then we're restricted by the budgets that are available for research. I think that is an area where computation as a technology purely is going to be able to transform the profession quite a bit. If architects no longer think in terms of one-off, but start to think about designing objectiles, basically flexible setups that allow to be deployed in multiple scenarios and contexts, and if that mindset would be appropriated, then costs in developing that R&D could be spread over a much bigger outcome, and that has a high potential. That shifts the role of the designer, the role of the author, in some people that become the designers of the system or of the objectile, and then people that are the ones that would deploy it or apply it on site. And so there's an opportunity there for the profession itself to potentially split up in different specializations, whereas one of the specializations has maybe more access to all the back of house work, which means they can, roles that are now maybe given to consultants can be incorporated, and there the architect has a huge power in reclaiming a lot of the area that he lost in the design team in the last century. That would be one area, and then in the other parts where these objectiles that are much more performative are deployed, because they are flexible, again, the architect may have a larger opportunity in applying them more appropriately without the monotony that you were talking about. So I think it's primarily the concept of the traditional Renaissance man of the architect that needs to be rethought. And design in that new world is still very much applicable. It's more in the agency of the creators that there needs to be a rethinking, and technology will facilitate that.
So how does construction begin to scale up? So we've seen the examples of robots bending plates. While at the same time, we're seeing people steel welding to get grasshopper generated plates into place. How does the construction industry begin to sort of keep pace with the digital advances that architecture is making? What are the successes you guys have seen in that, and then what are the real challenges that you might see in sort of robotics moving forward and picking pace?
We all want to answer, we don't want to answer. I think it comes from two directions. I think it comes from things that my colleagues have touched on, which are adventurous contractors, or contractors who are willing to go out and take the risk to do a project, that may invest in a specific type of tool or technology that would allow them to do it. And then I think it also comes from designers who don't design in a bubble, right, that are just taking the geometry that comes out of a Maya animation and then sending it directly to a contractor in the Pearl River Delta, but designers who retain an understanding for materials and tolerances and the labor conditions where these buildings are being built. So I think, it's not there's no one single answer to it. I think innovation comes from both sides, from the construction side and from the design side, and probably in reference to Christoph's last answer, from all of the consultants and architects working in between, who are kind of now working in the field between the original concept design and the finished product, right? All of this kind of depth of consultative and redesigning services and positions that now exist within the design and construction realm.
Yeah, I think, Sean, you just mentioned to me earlier that 80% of the construction in the next how many years is going to happen in this part of the world. From the people that are going to be building that, I think more than 80% are first generation on-site labor, on-site craft, and they were probably, by the vast majority, were probably farmers just before. So the skill that's available on site and the tradition, the craft, is virtually max a generation old, and more often than not probably non-existing. So I think this battle of how we can increase the quality of construction has to be fought on two fronts. On the one end, there's the pioneers like Zaha, like RoboFold, who are doing very exotic experiments that have extremely high potential, but the germination time for those will probably take a few decades. In the meantime, I think the strategic appropriation of the technology that doesn't per se rely on complex fabrication has in my opinion, has a much higher potential or much higher output. What you can do nowadays with an efficient design workflow and a simple plotter, and there was I forgot the name now of the architect who came up with this idea, where he realized that the people that were laying bricks were all listening to their iPods, so he made this iPod riff that basically told them which type of color brick they would need to lay as they're laying it, and automatically he would have a human-driven printer that would print drawings in brick walls out of different brick materials, just by hacking into the technology of the people that they were already using. There's things like a $100 laptop available, what we have on our phones, GoPros, all these things the technology is becoming extremely cheap, but it's how that gets appropriated in a workflow that doesn't per se rely on the high-end fabrication technology that I think will have the biggest impact down the line. So a combination of low-tech construction with a very strategic high-tech driving process, I think can have a huge impact now in the next decades, while waiting for the RoboFold to come in.
Okay, I'm aware that we're running long because it's just been fantastic. Nobody's wanted to say anything, and I'm sure there may be some other questions in the crowd, and I think our speakers will be willing to hang out. I'm also aware that our photographer would like a better angle to get the speakers and all of you. So maybe I could ask the three of you and Ted to come forward, and all of you to stand up and join us for a group photo before we make it a smaller conversation.